In this video, we want to continue our discussion of the inverse trig functions by specifically focusing in on their associated differentiation and anti-differentiation formulas. So to do so, we're going to start off with the arcsine function and go through the steps that one would need in order to come up with its derivative. So much like the steps we used to differentiate e to the x, we are going to use properties of the inverse functions and then implicit differentiation. So we start off with y equals arcsine x, and note that this statement can equivalently be written as sine of y is equal to x. You just take the sine of both sides, and the sine of arcsine of x gives us back to x. And once we do so, we've used our properties inverses. Now we can differentiate implicitly. The idea being, I don't know how to differentiate arcsine to get started, but I certainly know how to differentiate sine. Because it's a y variable with respect to x, the derivative is implicit. So we differentiate sine y exactly as we would like to, cosine y. Because it's an implicit derivative, we put a dy dx, and the derivative of x with respect to x is 1. So that very quickly here, we have dy dx equals 1 over cosine y. However, this is not quite what we are looking for, because we started off with the function y equals arcsine x, and we want a differentiation formula, so we want to write dy dx solely in terms of x. So let's draw a right triangle that I think will help us determine the value for cosine y. So we started with sine of y equals x, and what I picture from this is a right triangle, so we have our angle y. And if sine of y is x, we have this opposite leg x, and the hypotenuse being 1. So the remaining leg by the Pythagorean theorem would be the square root of 1 minus x squared. So cosine of y would be adjacent square root 1 minus x squared over hypotenuse. So we can take this value for cosine y and substitute it in. So the derivative of the arcsine function that we are looking for is 1 over the square root of 1 minus x squared. So we have the following differentiation formulas for the inverse trig functions. We have the derivative of arcsine, which we've just developed. And you can use similar steps to differentiate the remaining trig functions. So let me note with the first two formulas, in order for domains to make sense with that derivative, we have minus 1 less than x less than 1. And for the bottom formula with the derivative of arcsecant of x, we have the restriction that we need in order for the formula to make sense, the absolute value of x to be bigger than 1. And these formulas, especially the top three, are formulas we use frequently, and I would say you just need to know these formulas. But ideally, through practicing them, you will know them. So the associated anti-differentiation formulas. So in terms of integration, the arcsine and arccosine differentiation formula up to that minus sign are essentially the same. So there's really only one associated integration formula, one for arccosine. Then you have the arctan formula. And we'll encounter both of these in examples, but let me note that you can extend these, and it would require a u substitution. And if it's a squared minus x squared, you have the associated form for arcsine. And then a squared plus x squared, you have the associated formula for arctangent. And once again, just like the differentiation formulas, these are formulas that we will encounter frequently, so you want to make sure that you practice these enough that you're familiar with them and you will remember them when necessary. So let's investigate a few examples with differentiation. So let's start off by differentiating arcsine of the quantity 3x minus 1. So as a reminder, since this is something that we encounter frequently, when you differentiate arcsine, this is 1 over the square root of 1 minus x squared. So dy dx, this is a composition. We have the outside function arcsine, the inside function 3x minus 1. So the chain rule tells us we take the derivative of the outside function, 1 over the square root of 1 minus something squared. We evaluate this at the inside function, and then we multiply it by the derivative of the inside function, 3. For our second example, the tangent inverse of x squared. And note, the tangent to the minus 1, for us, that's never going to be 1 over tangent. It's always going to be the inverse of tangent. So similarly, let's remind ourselves, the derivative of arctangent, so I'll say tangent to the minus 1, so inverse tangent, 1 over 1 plus x squared. So once again, this is a composition. Outside function tangent, inverse, inside function x squared. The chain rule tells us to take the derivative of the outside function, 1 over 1 plus something squared, evaluate at the inside function, and multiply by the derivative of the inside function. So that would be 2x as our numerator over 1 plus x to the 4th. Lastly, a differentiation example involving the arc cosine. And as our reminder, the derivative of arc cosine, so say cosine inverse, is similar to the sine, except it's off by a minus sign. So minus 1 over the square root of 1 minus x squared. So for dy dx in this case, we're going to need the product rule to get started. So let's just write that out. We have the derivative of the first function multiplied by the second, plus the first times the derivative of the second. And now we just need to evaluate the two remaining derivatives. The derivative of x is 1, so it's arc cosine of x squared. And the second derivative, we once again see it's a composition. We have that inside function x squared, outside function inverse cosine. So we take the derivative of the outside function, so that would be minus 1 over the square root of 1 minus something squared. We plug in the inside function x squared, and we multiply by its derivative. And just to simplify a smidge here, we have the inverse cosine of x squared plus x times minus 1 times 2x would be minus 2x squared, all divided by the square root of 1 minus x squared squared, which is x to the 4th.